We talked about the different types of intermolecular forces, and now we're going to look at the effects of intermolecular forces. And so, as the title here suggests, we're going to look at surface tension, viscosity, and capillary action. This is a spider web with dew droplets on it, and the spherical nature of the water droplets are due to surface tension. And here, this is floating a paper clip on water, which if you have a really clean container, absolutely no soap, you can do it too. You can also float a needle on water. And as you can see, it looks almost like there's a skin on the water that's pressing down, and that's basically what the surface tension is doing. Here's another example of surface tension. This is a fisherman's fly floating on the water. This should sink because it's more dense than water, but it doesn't. So surface tension, what is that? It's the tendency of liquids to minimize their surface area. And of course, you can quantify that. We're not going to do that, but it would be the energy required to increase the surface area by a specific amount, and this is the surface tension of water. But surface tension allows things to float, like those little water skater bugs and other things as well. So what's going on here? Well, if we look at a water molecule down in the middle of the water, it's going to be attracted to multiple different neighbors. So we're looking at a two-dimensional drawing of water, not 3 dimensions. So we can see that this is close enough to interact with 6 other water molecules, whereas this one is interacting with only 4 neighboring molecules. Because it's interacting with fewer neighbors, it has higher potential energy, it's less stable. And so if we were to increase the surface area, say by putting something into the water and moving the water apart, increasing the surface area, that means that you get more surface molecules with higher energy. And that's not what happens. Things don't go towards higher energy, they go towards lower energy. So liquids tend to minimize their surface area. The surface area will be at a minimum in a sphere. And so this is a picture of that guy on the space station, and this is a really big droplet of water, and you can see without any gravity, it's round, right? It's a sphere. When we look at droplets of water hanging off this spider web, they're mostly round, but they're pulled down a little bit by gravity, right? And if you watch water drip off of off your burette, right? You see that droplet and it has that teardrop shape, right? That's because the gravity is pulling on it and it's distorting it a little bit. There was something else I wanted to say. I can't remember. Well, any questions about surface tension? Viscosity. I guess I watched too much television as a teenager or something. Every time I hear the word viscosity breakdown, and there were all these oil commercials, and they were always talking about viscosity breakdown. What's viscosity? It's the resistance of a liquid to flow. So you can think of it as how thick is the liquid, right? If you think about water versus honey, honey is thick and it pours slowly, right? Honey is viscous and water is not very viscous. We also have a unit to measure viscosity. Viscosity will be greater in substances with stronger intermolecular forces because you can think of the molecules as being stickier. For water to flow, the particles have to slide next to each other, right? And if they're stickier, that's going to happen more slowly. So molecular shape will affect this. Here we can see this with the normal alkanes. Their molar mass is increasing, but also the length of these chains. And they're not just straight molecules, they're kind of like cooked spaghetti, and so they can actually tangle around each other. And we see that the viscosity also increases as we go down there. Viscosity does depend on temperature. At higher temperatures, the molecules have more kinetic energy, and so they're able to partially break those intermolecular forces more easily, and the liquid becomes less viscous. So if you heat up your pancake syrup, it gets all watery, right? Really thin. Whereas if you have it in the refrigerator, it's going to be really, really thick. Well, this can be a problem in the engine of your car. Cars need motor oil. Hopefully everybody knows that. You gotta put oil in the car, right? What does it do? It lubricates the parts. The engine gets hot, and so we need the viscosity of the oil to be appropriate so that it is viscous enough to stay on the parts as they're moving and not just fall to the bottom, but also thin enough or inviscid enough that it's able to move around. Because you wouldn't want to put like paste in there, right? That would make it stickier, not slipperier. So cool thing is the modern synthetic motor oils. So these have polymers in them that will coil up at low temperatures, which would decrease the viscosity, and they will unwind at higher temperatures to increase the viscosity. And so you can get an appropriate viscosity range that's much larger in temperature difference than just like regular natural oil. This is just showing us how, as the temperature increases, the viscosity decreases. Capillary action. So this is someone having a blood sample taken, just a small sample. And, they prick your finger, and then you touch this little capillary tube to it, and the blood just runs up the tube. Nobody is sucking on it or anything, not like a pipette. It just goes up there all by itself. It's called capillary action, the ability of a liquid to flow against gravity up a narrow tube. And here we see different diameters of tubes. This is not blood, this is just a red liquid. And we see that the narrow tube, the liquid will rise much higher than in a wider tube. So capillary action is due to a combination of two different forces. We have cohesive forces, which is the attraction between molecules in the liquid, which is has to do with the intermolecular forces between the molecules of the liquid. And then we also have adhesive forces, which is the attraction between the liquid and the surface of the tube. So depending on what this tube is made out of, you may see higher or lower capillary action. If the liquid, like this liquid, appears to really like this glass tube, the adhesive force pulls it up, and then the cohesive force causes the rest of it to come up along. So if the adhesive forces are stronger than the cohesive forces, the liquid will rise. And this is also what gives us the meniscus. Okay, we've been talking about the meniscus in lab. So here is water in a glass tube, and it's got a meniscus. It's like almost looks like a contact lens floating on top of the liquid. The water pulls up on the edge of the test tube, or on the burette, or on the graduated cylinder. That's the adhesive force of water is attracted to the glass, and so it's trying to creep up the glass. Gravity keeps it from going very far. So this is called a concave meniscus, We have strong adhesive forces. Here, this is liquid mercury. Mercury's meniscus is upside down. It forms this bulge because the cohesive forces are stronger than the adhesive forces. The mercury doesn't like the glass. It would prefer to just go down into a sphere. Any questions? So you can have glassware made out of plastic that will have a flat, there will be no meniscus for water because it doesn't really have any attraction, and so you'll just see it be flat. But glass, you're always going to see this concave meniscus.